So we've got an increasing sequence of real numbers working over the reals. It's bounded above. We want to show that it's convergent. And so let's jump into the proof. So let's go ahead and say the following. Let's say assume that our sequence a sub n is as above. Okay. And let's let a equal the range of this sequence, so the set of a sub n where n equals 1 to infinity. Okay, so let's go ahead and note that since the sequence is bounded above, since a sub n is bounded above, there exists some positive number m such that what a sub n is less than or equal to m for every n in the naturals. Normally, you could also replace bounded above. The monotonic sequence theorem says that if you're bounded, right, if you're a monotonic sequence that's bounded, the difference between bounded above and bounded for the reals is a matter of absolute value. So bounded, you throw an absolute value in. Bounded above, you just take off the absolute value. It doesn't really matter. If you're bounded, you are bounded above. So we're going to go with that. Okay. So the point is, if the sequence is bounded above, you have this. So we want to go ahead and add, if the sequence is bounded above, then the set, the range of the sequence, the set A is also bounded above. So let's see, we've got an m such that this thing holds for all m, for all n. So we can say, so the set A is bounded above as a set. That's exactly what it means for this set to be bounded above, is that every element in A is bounded above like that. So we can say, thus, the completeness axiom implies that A has a least upper bound. Let's say, I don't know, let's call it S. Let's let S be the sup of A. Okay? And so the way this proof works is we're going to show that this sup of the set, the least upper bound of the set, is actually the limit of the sequence. And so let's just go ahead and say we will show that the sequence a sub n converges to S. So along those lines, we're going to go ahead and say, all right, choose an epsilon greater than 0. You've chosen an epsilon greater than 0. Now, in the back of my mind, I'm remembering the definition of a sup. The definition of a sup was if you take the tiniest little bit off of the sup, if you subtract the tiniest number off of the sup, you can find something in your set that's bigger than you. So you're the least upper bound. That means the tiniest little movement, and there is an element of the set that's greater than this difference. And so choose an epsilon bigger than 0. And we're going to go ahead and say, okay, so then and I've got to check my numbering. I believe this was lemma 2.4, I think. And this may vary. I'm posting this in 2022. This could vary year to year. But by lemma 2.4, there exists some element an in A. I'm going to go ahead and use the big N because I know up my sleeve I need the cutoff point for the sequence. So there exists a sub n in A such that S minus epsilon is strictly less than a sub n. Okay. Now, we want to show convergence, so I need to come up with the big N for the convergence, the cutoff point for convergence. So I'm going to use this particular N. I'm going to say then, if little n is greater than or equal to big N, and where I want to get from this is I want to get the distance between a sub n and S needs to be arbitrarily tiny. It needs to be less than epsilon. That's the goal. And if I've done that, then I've shown this thing is convergent. So then if you pick something bigger, first off, because the sequence is increasing, let's go ahead and say, since a sub n is increasing, you have a sub big N is always going to be less than or equal to a sub little n. So now we have S minus epsilon is less than this, which is less than or equal to this. for all n greater than or equal to our cutoff point. And now we just have to play around a little bit. So I'm going to look at moving the a sub n over here and the epsilon over there. And so let's just say, so in particular, I get s minus a sub n is less than epsilon. You know this is positive, actually. This is bigger than 0. Maybe we'll add here, this is bigger than 0. Why? Because s is the least upper bound of this set. It's an upper bound of all the a's, so it's bigger than or equal to everything here. And so this difference is positive. And in particular, this tells you that the absolute value of s minus a sub n is less than epsilon. That absolute value is, we usually write it like this, but it's the same because absolute value of a difference is a distance. This is a metric, and so you can write it either way. I mean, just by properties of absolute value as well, but the point is this is a metric. And so we've got what we want. So when you're beyond the cutoff point, this happens, and we've got less than epsilon. So that's the proof. So we should end by saying, thus the sequence a sub n converges to S. All right, so that's this theorem. In the next video, I'll do one more. I want to prove that every convergent sequence is Cauchy regardless of the metric space.